This video is about the third type of passive components, inductors. The first two were resistors and capacitors. Capacitors were based on electrostatic fields in insulators. Inductors are based on magnetic fields in conductors. If we take any conductor, we will put a current through it. That current produces a magnetic field around the conductor. And the magnetic field's strength is proportional to the current. Furthermore, if we have a conductor in a changing magnetic field, we'll get a voltage. And that voltage that we get is going to be proportional to the change in the magnetic field. Now, there's two ways that these phenomena get used in electronic components. We can have the conductors, the one which has the current going through it, and the one that is producing the voltage, either being the same or being two separate conductors in the same magnetic field. If we have two separate conductors in the same magnetic field, we get what's called a transformer. We won't be looking at transformers in this class. Instead, we'll be looking at the case where we have the same wire, the same conductor, being used both for producing the magnetic field and reacting to the magnetic field. This is the case known as self-inductance because it's the same wire in both cases. So what we have there then is that the voltage is proportional to, combining these two things, just proportional to the current with respect to time, the derivative current with respect to time. And if we write down the constant of proportionality there, it's usually abbreviated as L, and that L is the inductance, or more properly, the self-inductance. What can we do with this formula? Well, one thing we can do with it is the same thing we did with the similar differential equation that we had for capacitors. And that is, we can put in a sinusoid. So if we have V equals L times di dt, and we make that current now be a sinusoid, e to the j omega t. Then the derivative of the current with respect to time, that's just j omega e to the j omega t, or j omega I of t. Combining these two formulas, we get V equals L times j omega I of t. Or, if we want to know what the impedance is, remember that the impedance is just the voltage divided by the current. And for that, we're going to get voltage divided by current is just j omega L. And that formula is the crucial formula for doing all sorts of electronic analysis with inductors. It's the one formula really worth memorizing about inductors. Let's take a look at what we've got sort of in the complex plane here. So if we take the y-axis and the j-axis, if we have a resistor, that's just a constant position on the real axis, doesn't change with frequency. If we have an inductor with impedance j omega L, well, that's going to start here at 0 and go up with increasing frequency. In contrast, you might remember that capacitance had an impedance of 1 over j omega c, which can also be written as minus j over omega c. So there we started at minus infinity And as frequency increased, we moved along the negative imaginary axis towards 0. So these are capacitors down here, inductors up here. And on the positive axis, resistors. Notice that as we increase frequency, we're always moving up in the complex plane, whether we're talking about capacitors or inductors. Okay, I think that's enough for today's video. We'll look in future videos at how you can affect the inductance of a wire, and we'll look at what happens if we combine inductors with other components. But for now, memorize this formula. Z equals j omega L. The impedance is J times omega times the inductance. That's it for now.